Okay, so in this particular kinematics problem, we have an airplane initially at rest as shown in the diagram. It is going to accelerate down the runway in order to attain takeoff speed, which is given to us as 250 kilometers per hour. And the problem states that the airplane is accelerating at a constant rate of 2 meters per second square. Okay, and here is part A, B, C, D, E, F, and G. All right, so let's go ahead and get cracking. I will show you how to do part A and B on the slide. To find A, to find the length required to reach this particular takeoff speed. The length here in this case is just represented by the letter D in the schematic, but you can call it whatever you want. You can call it X, L, whatever you want it. Alright, so keep in mind length is a scalar quantity, and the airplane is only moving in one direction to the right of the screen in order to take off. So in this case, because the plane is moving one way, the distance is the same as the magnitude of the displacement. Displacement is just distance plus the direction, but here we're asked to find length, so all we have to do is find the distance. Alright, so right away I noticed that the unit for the takeoff speed is in kilometers per hour, but then the unit for acceleration is in meters per second square. So it's a good rule of thumb to convert all units from the get-go, so this way there's no hiccups later. So to convert 250 kilometers per hour to meters per second, the first step I did was convert kilometers, which is 1 kilometer for every 1,000 meters. The kilometer on top and bottom is going to cancel out. And then I don't want hours, I want to go to seconds. So therefore, since the hours is in the denominator, and then my third fraction here, I would need hours on top, but then on the bottom, I need seconds. But for every hour, I have 3,600 seconds. So I bypassed minutes here. I just went straight from hours to seconds. Okay, so units cancels out there, and then if you simplify it in a calculator, you will get 250,000 meters divided by 3,600 seconds, and that simplifies down to about 69.44 meters per second. All right, the easiest way to find part A, I think, is just to use this particular function in kinematics. It is time independent. Plus, you kind of have everything already. You know what VI is. VI is 0. VF is given in kilometers per hour, but we just converted that to 69.44 meters per second. A is given as 2, so the only variable that's unknown here is our displacement. So we can find displacement, but displacement will give us the length of the distance needed. Okay. All right. Therefore, I left out VI squared because that's just 0. And then VF here is 69.44. We're going to square that. A is 2 as stated. And then here in this expression, the only unknown is your delta x. So 2 times 2 is 4. And then to get delta x by itself, we need to divide both sides by 4. So here's my work. 69.44 square is going to give us about 4,821.91 meters square or second square. And we're going to divide that by 4 meters per second square. And that's going to give us our displacement. So the answer is going to come to about 1,205.58 meters. Okay. All right. So here's how to do part B. To find the time required to reach takeoff speed. I think the easiest way is just to use the average acceleration equation here. Why? Because we're asked to solve for time. We know what A is. We know what VF is. We know what VI is. So really the only thing unknown here is delta T. But this is a little tricky. Delta T here is in the denominator. So to solve for delta T, we need to do algebra. So multiply both sides by delta T, but at the same time divide both sides by A. So really, essentially what you're doing is you're just switching delta T and A, the placements of them. Delta T goes up to the numerator, A comes down to the denominator, a little crisscross there. All right, and that's appropriate for this particular algebra step. All right, so therefore we have delta T is equal to VF minus VI over A. Again, we know what VI is. VI is just 0, so I just cross that out. VF is 69.44 meters per second. A is 2, and therefore if you simplify it in your calculator, you should get a value of about 34.72 seconds. Okay. But here's an alternative way. Again, as you practice, hopefully by now you recognize there are different approaches to solving problem. Be comfortable with these kinematics equation prior to your assessment. All right. The other way to do is using your displacement function. In this case, why can you use this? Well, you can use this because you know what delta x is from part A. We know what VI is. The airplane is just sitting at rest on a tarmac before it accelerates. We know what A is. So really the only thing left unknown here is delta T. So if we just kind of plug and chug, displacement, which is from part A, again, where my cursor is on the bottom left of my screen here in yellow, that's highlighted in yellow, I just substitute that in 1,205.58 meters. I cross out VI, so VI times T is just 0, and then I substitute in A for 2. But I notice here the 1/2 and the 2 is going to cancel out. 1/2 times 2 is just 1. So really I'm left with just the same value on the left side, 1205.58, and the unit here is second square because the second square needs to go up, the meters units cancels out. But you don't really have to worry about units if everything is converted, from the get-go. It will naturally cancel out, okay? Therefore, to solve for t, we need to square root both sides. This term on the right is t squared. To get rid of the square, we need to radical both sides. So therefore, radicalizing both sides will give us t, which is equal to 34.72 seconds. As you can see, the answer is the same. And if you're not sick of it yet, here's another way. If you want to use the average velocity functions, you can use this function because in this case, acceleration is constant. That would be displacement over time, which is equal to vi plus vf divided by 2. But again, here you notice delta t is in the denominator. So to solve for it, delta t has to go in the numerator. So what I like to do is I'd like to flip the whole function upside down just to get t in the numerator. And then here I left out vi because vi is just 0. So it would just be 2 over vf. Okay. And then to get delta t by itself, you multiply both sides by delta x. Therefore, delta t is equal to 2 delta x over vf. And if you plug values in, and if you want, you can do this, or you can just take my word for it. If you punch all this in your calculator, you will also get the answer of 34.72 seconds. So there are 3 different approaches, whichever you want. It should all work out. All right, let's do C and D. Here are a few ratio problems for you. Here, part C asks you to find the distance from the first second compared to the distance during the first 2 seconds. So from 0 to 1 and then from 0 to 2. And then part D asks us to find the distance from 1 to 3, compare that to the distance from 3 to 5. So it's important that as you do these ratio problems, pay attention to the intervals of time that's being compared. Okay, so let's do part C. All right, to do part C, I think the easiest way to do is using your displacement function again, because since the time here in part C starts from 0 to 1 and from 0 to 2, I will use my displacement function. I wrote it out for you to see, but then vi is just 0 because I'm starting at 0 second. At 0 second, vi is 0. So cross that out, and therefore the only thing left is just 1/2 at squared. Okay, and then we plug in a, which is 2. The change in time on the left side of the equal sign here from 0 to 1 is just 1 second. So the time interval is just 1. Again, 1/2 times 2 is just 1, and then 1 squared is just 1. So our first displacement is 1 meter. But keep in mind, why I solved for displacement here, you notice I didn't really include a direction because the question is asking us to compare the distance, which is just the magnitude of the displacement. So why I use the displacement function here, I don't really need to include the direction because I'm simply comparing the value, the length of the distance covered. All right? So I can use the same strategy. However, in this case, the right side of the equal sign for part C is from 0 to 2. Because I start from 0, my vi is 0 again. So here we just simplify down to 1/2 at squared again. But you notice here this delta x here is 1/2 times 2, and then the time interval here is 2 seconds instead of 1, because from 0 to 2 is a difference of 2 seconds. So make sure you pay attention to the time interval being compared. Okay. All right. So 1/2 times 2 is just 1, and then 2 squared is 4. So therefore we have the second distance, which is just 4 meters. So if we set up our ratio here, the left side is what we found, which is 1 meters. The right side, the equal sign, which is 4 meters. The question mark I just replaced with heart. In this case, to solve for heart, we would divide both sides by 4. Okay, so really here is just an algebra step. To get heart by itself, which is with a question mark, divide both sides by 4. 1 divided by 4 is 0.25, or you can leave it as 1/4, however you want. Okay, so that's the answer for part C. All right. And let's do part D. Part D here asks us to compare the distance between 1 to 3 and then from 3 to 5. So you notice here it didn't start at 0, it starts at 1. Over here it starts at 3 seconds. Okay, so we can use the same displacement function. The only thing you really got to be cautious about is the starting point. Here vi is not 0. Vi cannot be 0 for this particular part D because the statement on the left side starts at 1 second. So right away, I encourage you to write all your velocities out, as you can see on the top of my screen here. This one's pretty easy. The acceleration is 2 meters per second squared, which tells me that every second that goes by, the velocity increases by a rate of 2 meters per second. So it starts at rest, so the next second, it increases by 2, so it's going to go from 0 to 2 meters per second. And then another second goes by, my velocity gets faster by 2 meters per second. So it's going to go from 2 to 4, and then it's going to go from 4 to 6, and then it's going to go from, okay, actually, I don't even need to do any more because I notice here my initial time on the right side is just 3 seconds, so I can just stop at 3. I don't need to go to 4, 5, or 6. All right, so here I substituted in 2 because this particular problem on the left side of the equal sign, it starts at 1 second. At 1 second, the object's already moving at a rate of 2 meters per second. And then delta t is 2 seconds because from 1 to 3 seconds is a difference of 2 seconds. And that's where that 2 seconds comes from. And then here the rest is just plug and chug. 1/2, a is 2. Again, change in time here is 2 seconds. And then don't forget the square. And if you do all that, you'll get 4 plus 4. So that'll be 8. So how far did the airplane travel between 1 to 3 seconds? It's 8 meters. Now we need to find this right side, in order for us to find the question mark. So here on the right side, the time starts at 3 and it ends at 5. Because it starts at 3, we can use the displacement function again, except in this case, we need to focus our attention on VI. VI starts at 3 seconds, so therefore my VI is 6 meters per second, not 0. Don't make that rookie mistake where you plug in VI as 0. It's important and it's crucial to pay attention to where the time starts and stop. Alright, here my delta t is 2 seconds because from 3 to 5 seconds is 2 seconds. My acceleration is given again, and then the delta t on the right is also 2 seconds. And then we square that and we simplify those in the calculator. 12 plus 4, which is 16. Therefore, we have the statement. We have 8 meters is equal to blank 16. So what does heart have to be to make that a true statement? Well, if your basic math is good, heart has to be a half, right? Because a half times 16 is 8. 8 equals 8. Or if you want, you can just simply, to solve for heart, divide both sides by 16 to get heart by itself. So therefore, 8 divided by 16 is just 0.5, okay? But here's another way to do C and D by using ratio. And I think I like this way just because it's quick. But if you're not confident with how to think about quadratic functions, then maybe watch this segment a couple times and hopefully it makes sense, okay? All right, here I have chosen for part C, the first time interval is from 0 to 1. I've chosen that as my reference point, or something I reference as my baseline from 0 to 1. So in the diagram, this little segment is the distance, which I'll call x1, and that takes 1 second, from 0 to 1 second. I don't know what it is. I'm just going to call it x1. It doesn't really matter to me, okay? So therefore, the displacement function for x1 simply reduced down to 1/2 at1 squared. Now, what happened to the VIT? Because it starts at 0, my VI is 0, so that VIT term disappears, so it just leaves me with this. And then what it allows me to do, though, is it allows me to compare, well, where would it be at 2 seconds, right? So on the right side of the equal sign, it says from 0 to 2 seconds. Well, I can call that distance x2, okay? Therefore, it reduces down to the same function. Because I start at 0, my VI is 0, so VIT cancels out. So I can just write the function as 1/2 at2 squared. But this is the important skill here. Well, t2 is just 2 times t1. From 0 to 1 is 1 second. From 0 to 2 is 2 seconds. So if the left side of the equal sign is t1, then the right side of the equal sign must be twice as much. So therefore, I can replace with that. I can replace t2 with that true statement. So instead of writing t2, I can substitute t2 for 2 times t1. So make sure this is a true statement before you proceed. And then the square is outside the parentheses. And then therefore, you need to distribute the square. So 2 squared is going to give us 4. And then t1 square is just t1 square, okay? So this is where the 4 comes from. The 4 comes from taking 2 and then squaring that because it tells you to do so. 2 times 2 is 4. All I did was I pulled the coefficient 4 outside of the statement. And then I carry down the 1/2, I carry down the a, and then t1 squared is just t1 squared. But what you do notice here is the 1/2 at1 squared, it's on the left side here. 1/2 at1 squared is x1. So I can say x2 is 4 times x1. Because all this junk right here, 1/2 at1 squared, is x1. That's my reference point. Okay. And now it's 4 because it's a quadratic function. So doubling the time is going to cause your displacement to increase by a factor of 4, not 2. That's a common misconception that kids have. Okay. All right. So you notice here what came up on the screen. So that line right there, that distance right there would be 4x1. Okay. So hopefully that makes sense. And if that does, use it. If not, just crank out numbers then. Okay. Therefore, on the left side, I can just call it x1. On the right side, I just solve for it, which is 4x1. And there's my heart, which takes the place of the question mark. And then to get heart by itself, I need to divide both sides by 4. And if you're doing this in terms of variable, you notice x1 on both sides will cancel out. So therefore, canceling x1 out right here, which is leaving a 1, dividing both sides by 4 would reduces down to 1/4, which is 0.25. So I can see this answer is the same as the previous slide. So if you need to go back to the previous slide and watch how I got 0.25. Okay, I like this approach because there's no calculator work really, except for just knowing how to do ratios. All right, let's do part D. Okay, for part D, to do part D quickly, I noticed that it went from 1 to 3 and then 3 to 5. So here on my screen, this arrow that just came up, that to me is when t is equal to 3 seconds. Now, why is there a 9 in the front? Well, if you go from 0 to 3 seconds, that's 3 times the initial time, which is just the first reference point of 1 second. But if it's 3t1, you're going to square that coefficient. So 3 squared is going to give you 9. 9 what? 9 times the original distance. Okay, and I can use that same skill and the same strategy for 4 seconds. Well, if you're going to accelerate for 4 seconds, your displacement is actually multiplied by a factor of 16 compared to the first second. So 4 squared is 16, and it's 16 what? 16 times the baseline, the reference point of the first second. And then last but not least here, I'm going to take it all the way to 5 seconds because I notice here in part D, the highest time interval here is 5 seconds. Okay. Therefore, the distance cover, or the displacement cover in this case, will be 25 times x1. So here's the little x1. So if you go from 0 to 5 seconds, the displacement cover is actually 25 times that amount, not 5 times, because it's 5 squared and 5 squared is 25. Okay, and again, that has to do with the displacement function. So if you need to watch this segment over, hopefully you can exercise that. All right, but you notice here, I call it x1 to 3 because that's the interval 1 to 3. And then here, x from 3 to 5, which is denoted using subscripts there. But this one is pretty easy. Well, if it wants the distance from 1 to 3, well, I know the first distance is already x1, and that took a second. But I know from 0 to 3 is a distance of 9x1. So the difference here between 9x and x would just be 8x. Okay, so on the left side, I've covered a distance of 8x. Now on the right side, it says from 3 to 5. Well, if I look at the diagram, from 0 to 5 is a distance of 25x1. But then from 0 to 3 is a distance of 9x1. Well, here's my green arrow, or the rest of the length. What does that have to be to equal to 25x? So in this case, you can use common sense. You can say 9x1 plus 16x1 would give you the whole entire length from 0 to 5 seconds. Or you can simply take 25x1 minus 9x1, which will give you a length of 16x1. Okay. Again, I like the strategy just because I can add and subtract quickly as long as you can do ratio. Therefore, on the left side equal sign, I can replace it with 8x1. On the right side, I can replace it with 16x1. The x1 is going to cancel because I don't know what x1 is. Again, it's arbitrary. I don't know what it is. It's just some unknown value. And then here's heart, and therefore to solve for heart, I would just divide both sides by 16. So 8 divided by 16 will give you 0.5, which is consistent with what I got on the in the previous slide. Okay, so watch this segment again. Hopefully exercises. It'll save you time. But if this is complicated for you, maybe just stick with the crank out numbers. All right, here's part E. Part E asks us to find the ratio for the average speed between 2 to 4 and then 3 to 6. So to do this one, we can just apply the average velocity function, which is Vf plus Vi divided by 2. Now, keep in mind that the airplane is only going one way. Because the airplane is only going one way, average speed and the magnitude of average velocity will be the same. Hence, while the variables are different, I can use the same equation, because I'm just looking for the value of the speed, or the magnitude of the velocity, which is just speed. All right, so here we have Vf plus Vi divided by 2, and then again, if you know your velocity, simply just by adding 2 in this one, because the acceleration is 2. I've gone all the way to 6 seconds here, because I noticed here in the highest time interval is just 6 seconds. Therefore, the first part is 2 to 4, so I want to zoom in at t is equal to 2. My velocity is 4, and then at t is equal to 4, my velocity is 8. And then so therefore I can substitute that in. Vf is 8, Vi is 4, the 2 is part of the function. So 8 plus 4 is 12, 12 divided by 2 is 6 meters per second. Now, the next part, which is on the right side of the equal sign, is from 3 to 6. So I'm going to zoom in on 3 second. At 3 second, my speed or my velocity is 6 meters per second. And then at 6, my velocity is 12 meters per second. So therefore I can substitute these values in. 12 plus 6 is 18. 18 divided by 2, which is 9 meters per second. And if you do that, you'll get on the left side, which is 6 meters per second, equals to heart. And then on the right side, we just calculate, which is 9 meters per second. The solve for heart, divide both sides by 9. Therefore, you get 0.6666 running, or you can just round it to 0.67, or you can leave it as 2/3. It doesn't really matter. Okay. But here's another way to do part E. If you really wanted to, you can apply the definition of average speed, which is equal to distance over time. But we don't know what the distance is. We know what the time is. On the left side of the equal sign, the time is from 2 to 4, so the change in time is 2 seconds. And on the right side, we know that it's from 3 to 6, so the change in time is just 3 seconds. But what we can do is find distance using the displacement function. Okay. All right. So let's find d real quick. To find d, again, it's important that you know where the problem starts and stop. In this case, I'm going to go ahead and use the velocity at 2 seconds, because this particular part starts at 2 seconds. At 2 seconds, my Vi is already 4. My time interval here is 2. From 2 to 4 is 2. And then really it's just plug and chuck. Acceleration is given. Time, again, is just 2 seconds. And then if we do this, we'll get the displacement, which is 12. But again, it's 12 meters east, but we don't really care for the direction here. All we need is just the length of it, which is 12 meters, which is the distance. All right, so if we do that, we can just plug it back into the numerator. So therefore D is 12, and then 2 seconds. So the average speed for the first part on the left side, from between 2 to 4 seconds, is an average of 6 meters per second. And then we use the same function here on the right side of the equal sign, but here it starts at 3 to 6. So therefore, we can just use our displacement function, except our Vi now starts at 3 seconds. And at 3 seconds, the object is already moving at a rate of 6 meters per second. Okay, so Vi here is 6, and then delta T is 3, because the difference between 3 to 6 seconds is 3 seconds. So all this detail work here, you got to be on point, because if you're not paying attention to details, your calculator work it's going to come out wrong. All right, so if you simplify all this in your calculator, you should get a sum of 27, and then for distance we can plug in, excuse me, that's just 12, it should be 27. Okay, so let me just exit that. That should say 27, excuse me. Okay, alright, and this should say 3. I didn't fix that, excuse me. Alright, sorry about that. And so therefore our distance here is 27. The time interval here is 3 seconds, and then if you do 27 divided by 3, which is just 9. So if we do our statement again, average speed from 2 to 4, which is 6, equal, question mark I left as blank, and then the average speed from 3 to 6 is 9, and I'm going to replace that blank with heart. To solve for heart, again, you notice that it reduced down to the same statement, which is 6 over 9, which is the same value as the previous work. All right, and then let's do part F. Part F is super whack. It asks you to find the change in velocity. So here, we would just start with acceleration, which is equal to delta V over delta T, but I want to solve for delta V because it asked us to compare delta V. It didn't ask V average, it didn't ask VF, it didn't ask for VI, it just asked for delta V grouped together. So therefore I want to isolate for delta V by simply multiplying both sides by T. And then here, we can just do it twice. All right, the acceleration is 2. The first time interval is from 1 to 3, which is 2 seconds. And then on the right side, the interval is from 2 to 4, which is a interval of 4 seconds. So if we do on the left side, 2 times 2 is 4. On the right side, 2 times 4 is 8. And then all we have to do is set this two statement equal together with the question mark or a blank. And again, the blank is my heart. And then to get heart by itself, I divide both sides by 8. So 4 divided by 8 is 0.5. Okay. All right. And then part G is true. Conceptually, the average speed during each second increases as the airplane accelerates. In this case, as the airplane accelerates, it covers more distance because it's gaining speed during each second. So if you're going to cover more distance each second, the numerator would increase. The denominator stays the same because it's just 1 second. So S is equal to D over T. And D increases each second because the plane is moving at a faster rate. So if the numerator D increases, and the denominator stays the same, the answer has to increase. Okay, if you need to write that out. All right, other than that, I hope that helps. Good luck. Stay nerdy.